Thanks, Jesper, for the introduction. So basically, this talk is going to be about coming up with bit commitment protocols that are secure against adversaries that have access to quantum devices that are limited in some way. So as you might know, we're still a fairly long way away from being able to build general quantum computers, and even coming up with a quantum device that keeps its state stable for a fairly long period of time is still a very difficult research problem in experimental physics. Now, as cryptographers, there's always a silver lining whenever we're faced with a very difficult research problem. We can always assume that the adversary is also unlikely to come up with a solution in the near future, and base protocols on that assumption. So that's basically what we're going to do. And this talk in particular is going to be about a fairly general tool with which we can take an assumption on the quantum capabilities of an adversary and turn it into a proof for bit commitment protocols, a security proof. And it's going to give us essentially optimal bounds in many cases of interest. Now, for the sake of concreteness in this talk, I'm going to talk about a particular type of limitation of adversaries. Namely, I'm going to talk about adversaries that have perfect quantum memory, but only a limited amount of it, so they can't store everything. So let's get started. So as you all know, we can't just do bit commitment from scratch. If all we can do is communicate between Alice and Bob, even if the communication is quantum, we still can't do bit commitment without making some kind of assumption. Now, what kind of assumptions can we make? Well, there's complexity assumptions that we're all familiar with, or we can make physical assumptions, such as the adversary only has a bounded amount of storage, or the two participants are connected by a channel in which the noise is not controlled by any of them. And in this talk, we're going to talk, like I said, about bounded quantum storage. So the adversary can store an unlimited amount of classical data, but only a limited amount of quantum data. So here's what the model looks like in a nutshell. So we have Alice and Bob. They exchange quantum messages back and forth. And at some point, there's going to be a memory bound that applies. So at that point, we're going to suppose that both parties can only store at most q qubits. So a qubit is basically the quantum analog of a bit. And it turns out that if we make these assumptions, there's a protocol to do bit commitment such that the honest parties only need to do very simple quantum operations, like preparing a very small quantum state and measuring it at the end, which we can do with current technology. But to break this protocol, you need a substantial amount of quantum memory. And I should say also that if you're able to do bit commitment in the quantum world, you can also do oblivious transfer because there's a protocol to do OT if you have bit commitment at your disposal as a black box. So here's some history of this model. So the model was first defined in 2005 by Damgaard, Fehr, Salvay, and Schaffner. And what they had is that, so suppose so they came up with a protocol in which n qubits were exchanged between the two parties. And if we assume that all the adversary could do is store at most n/4 qubits, so a quarter, if the adversary could only store up to a quarter of the qubits exchanged in the protocol, then the protocol was secure. And this was later improved to a bound of n/2, and then later on to 2n/3. And using this, the techniques I'm going to present will make it to essentially the best possible thing you can get from this model. Namely, of course, if an adversary is able to store everything that happens in the protocol, it doesn't make sense to assume there's a memory bound. But we're going to show that as soon as the adversary is not able to store everything that happens in the protocol, that he's bounded, that there's a little bit of the qubits that he's not able to store, then the protocol is going to be secure. So this is obviously optimal. Now, the way it's going to work is that we're going to reduce bit commitment to something called weak string erasure. I'm not going to do this. This was done by König, Wehner, and Wuhlschläger in 2009. And the idea is that if you can have a protocol that implements this, which I'm about to explain, then you can do bit commitment. And this weak string erasure primitive works as follows. So it's a box that gives Alice a bit string, n bit string, and it gives Bob some random subset of the n positions and the corresponding bits at the index. So Bob gets a partially erased version of the string Alice gets. And we're going to call a protocol that implements this secure if we satisfy these two things here. So we first want that the subset that Bob gets is uniform, and Alice has no idea what it is and has no control over it. And we want that if Bob is dishonest, well, we want to make sure that he doesn't have full information about Alice's string. And we're going to formalize this by having this bound here. So this min-entropy here, you can view this as a measure of uncertainty about Alice's string given whatever dishonest Bob has. I'm about to explain this a bit later, but for now, just view this as we have some lower bound on the uncertainty that Bob has about Alice's string. And it turns out that if we can come up with a protocol for weak string erasure with even a tiny lower bound on this quantity, so as soon as we have a slightly non-trivial bound on the uncertainty that Bob has about Alice's string, then the protocol works. So before getting into the actual protocol, I'd like to take 2 minutes to explain all you need to know about quantum information just to see why the protocol might work. So first of all, a qubit, that's the quantum analog of a bit. Well, you can think of it as a photon that is polarized at any angle. So just think of it as an angle like this here. Now, what's quantum about this is that we're not allowed to just measure this angle directly. All we're able to do is to whenever we try to measure it, is to basically ask a question. Like, we get to pick an angle, let's say this angle here, and the answer we're going to get is whether it's at this angle or an angle perpendicular to it. So we get an answer that's either this or this, and we get to pick many angles. And if you, let's say, do this measurement on a photon that is polarized, let's say at an angle that's close to this angle, then we're more likely to get this answer than this answer. And in fact, all you'll have to know for this protocol is that, let's say you have a qubit that is, let's say, horizontal, and you measure in the horizontal-vertical basis, so you ask whether the photon is horizontal or vertical, then you'll get the right answer with probability 100%. Now, if you do the same measurement, but you input a photon that's 45 degrees off from the question you're asking, then you'll get a random answer. You'll get either horizontal with probability 50% or vertical with probability 50%. And in our protocol, what we're going to do is that we'll encode bits into qubits in 2 possible ways, so in 2 possible bases. So the first one is going to be the plus basis. So basically, we'll encode a 0 into horizontal and 1 into vertical. Now, we can decode this just by doing the appropriate measurement. But we will also encode it into the x basis, or the diagonal basis. So 0 is going to be diagonal in this way. 1 is going to be diagonal in this way. Now, so if we try to measure in the plus basis and we've encoded in the diagonal basis, then we'll get a random answer, and vice versa. And if we measure in the right basis, we get the right answer. So this is basically all you need to get the intuition from the protocol. And this is our protocol for weak string erasure. So how is it going to work? Well, Alice is going to pick a random string, xn, and she'll also pick a random string of bases. So she'll pick a string of n plus or diagonal basis. And what she'll do is she'll encode the string x into this string of bases. So if the first x is 0, and the first basis choice is, let's say, diagonal, then she'll encode 0 in this diagonal basis, and so on for all of them. And she'll send this over to Bob. And Bob, what is Bob supposed to do with this? Well, he'll also pick a string of bases independently and measure in that basis. Now, since Bob's basis choice is independent from Alice's, well, he'll guess the right basis half the time. And whenever he gets the right basis, he'll get the right answer. Whenever he picks the wrong basis, he'll get a random choice. So, and here, after doing this, we'll wait a while. At this point, the memory balance is going to apply. And then Alice is going to send her choice of basis over to Bob. So that at this point, Bob is going to be able to determine at which positions he guessed correctly, which positions he guessed wrong. And then his output is just going to be, well, the subset where he guessed correctly and the bit values corresponding to that. And Alice's output is just going to be the string she picked in the first place. Now you can see that this intuitively does what we want, right? Bob gets a random subset of the bits that Alice picked. Now, so does this protocol satisfy the security definition I gave earlier? You remember that there were 2 points to this. The first one was that the subset had to be uniform and independent. Well, that's clearly satisfied because the subset only depends on the XOR of the 2 strings of basis choices. So Alice has no control over it. And now the second point is a bit trickier. We need that for a dishonest Bob, who does anything he wants, we need to ensure this min-entropy condition is satisfied. And so this is what our theorem is going to address. We'll have a tool that allows us to get lower bounds on this quantity in fairly general settings. So not just this bounded memory setting, but other types of physical limitations. So now I'll talk a bit about this min-entropy. So I guess this should be fairly familiar to you. So so first we'll look at the min-entropy of a classical random variable. So let's say this is our probability distribution. And the min-entropy is just going to be the log, minus log of the probability of the highest probability outcome. And in other words, you can view this as minus the log of the probability of guessing x if you don't know anything about x. Because of course, if you're asked to guess x and you have no information about it, well, you're just going to pick the most likely outcome and go with that. And now this suggests a definition for the conditional min-entropy. Now, let's say we want to define the min-entropy of x given b, so the uncertainty that someone who has access to b has about x. Well, we can still define it as the minus log of the probability of guessing x, but now given b, right? You look at b, and then based on that, you make a guess as to what x is. And if b is quantum, well, this definition still makes sense. What we can do is that it's going to be the probability of guessing x after doing the optimal measurement on b. So you look at your system, do the best possible measurement you can do, and then try to guess based on that. So that's going to be our definition of this. And we'll actually be interested in the case where both x and b are quantum. So now it gets a bit trickier because it doesn't really make sense to guess what a quantum state is. But it turns out that there is a good analog of this. So one way to look at the guessing probability of x given b is that you're going to look at b, transform it somehow, and try to get a copy of x. And if you get a copy of x, then you've guessed correctly. Quantumly, what you can do is that instead of trying to get a copy of x, you try to get your whole state into what's called a maximally entangled state between x and a copy of x, of the system x. Now, I won't go into more details about this, except note one thing, is that somewhat counterintuitively, this can yield negative entropies. So classically, the min-entropy ranges between, let's say of n bits, ranges between 0 and n. Well, the min-entropy of n qubits can range between minus n and n. And right? And just a very short caveat for those in the know, our results are actually about what's called the two entropy and not the min entropy. Now, if that doesn't ring a bell, just think of it as h-min and forget the slide. Yeah. So here's the main result of our paper. And that's going to be a little bit technical, but hopefully it's just going to be the one slide. Our result is about getting lower bounds on the min entropy of channel outputs in terms of the min entropy of the two entropy of the channel inputs. So let's say we have some quantum operation that goes from, let's say, n qubits into some output system C, and we have a bound on the two entropy of these guys here, A1 to AN, given E here. And we're interested in getting a lower bound on the output of the channel given this extra system here, E here, that's not affected by the channel. And, excuse it's a bit technical, but yeah. So suppose that our channel has this nice linear decomposition here. So we can decompose it into a whole bunch of terms. Well, it turns out that there's a way to get a bound by splitting all of these terms into an easy to bound set and to a hard to bound set. And we get an expression like this. Now, this might not be so obvious that this is useful, but it turns out that when you plug in some interesting channels here, it's fairly easy to get interesting bounds out of this, and concrete bounds that don't involve maximizations and so on. Such as, for example, one choice you can make is to an M that takes your n qubits and takes a random samples out of them. So you get a random sample of k out of the n systems. And I'm not going to talk about this particular one, but except to mention that you can get results on quantum random access codes this way. Another thing you can do is plug in an M that takes each subsystem and measures into a random basis. And this is what's going to be relevant for to analyze our protocol. So more specifically, what our M is going to do is take each of the qubits with 50% probability measure the x basis, 50% probability measure in the plus basis, and tell us which basis it picked. And here's what we get out of this. So here, this is the two entropy of the output. So x is the measurement result, theta is the basis choice, and this is the two entropy that was before the measurement. So this is the quantum state before the measurement, and this is some extra system. And we get this sort of thing here. So just okay, I'll maybe speed up a bit. But basically, if we apply this theorem to our protocol, now this is our protocol where Bob here is dishonest. So we don't know what he does here until the memory bound. But at the memory bound, what we have is that we have a state here at Alice, and Bob's state here has only q qubits. And at the end here, we're basically in a setting where we can apply the protocol in that all that's left is that Alice measures in a random basis, and we need to get a bound from that. So we can just apply our theorem to that state at this stage of the protocol, and we basically get a bound immediately. And so if we turn the crank, we get this result where our bound is essentially, as soon as the bound is smaller than n by a small amount, then we get a secure protocol for bit commitment. And also, it also works not just in this bounded storage model, but also in any model where you can get a bound on that state in the middle of the protocol. Now, apologies if the end was a bit rushed, but hope that was still comprehensible. Thank you.